r minus 1/2 r squared, so it's a quadratic approximation to looking at the arithmetic mean and standard deviation. Proponents of the alternative risk measure need to get beyond their current line of argument. There's a large difference between my 1952 paper and my 1952 book.
Or 59 book. Yeah.
59, I'm sorry, my 1959 book. Thank you. The 52 paper, puts forth this mean variance analysis,
Yeah.
and it puts it forth both as a hypothesis as to how people do act and a normative recommendation of how people should act.
Mm-hmm.
By 1959, I've completely dropped the notion of a hypothesis about how people do act. I never say the word.
Yeah.
It's all normative. Then what is different, the big difference between 1952 and 59, one big difference is the justification for mean variance analysis.
Mm-hmm.
I had already, by the time I wrote the 1952 article, I already knew about expected utility,
Mm-hmm.
and I had, in fact, we talked about Friedman and Savage
Yes.
utility analysis,
Yeah.
and so on and so forth.
And
So I was already convinced that a person should act according, rational decision making was according to expected utility,
Mm-hmm.
Using probability beliefs when objective probabilities are not known. But I hadn't addressed the following question: if I believe that in expected utility, why am I pledging mean variance? And so this book, for example, the new book,
the risk return analysis.
Risk return analysis talks about mean variance approximations to expected utility. That was already in the 50. It was not in that was not in the 52 article. It was in the 59 book. Look at page 121, the table. The first column is return, like
Mm-hmm.
minus 0.3, minus 0.2 for 30% loss, 20%. Second column is the log of 1 plus return, like
Mm-hmm.
a Bernoulli utility function, the most ancient
Yeah.
utility functions. Then the third column is r minus 1/2 r squared, so it's a quadratic approximation to the logarithmic. And you'll see that from about a 30 or 40% loss to about a 40%, 50% gain, the two are almost indistinguishable.
Mm-hmm.
And so the expected value, one has to be the expected value. The other one is mean variance efficient. The other is a well-known utility function. So I never justified mean variance analysis by normality.
Yeah.
Nowhere.
That's an important
That's
point.
very important.
Yeah.
It was always mean variance approximations to expected utility, and there's been a tremendous amount of literature since then, almost all of it favorable to mean variance analysis.
Yeah.
And
particularly in those ranges you mentioned, right?
well, it turns out that I had two approximations,
Mm-hmm.
two ways of knowing the mean and variance and guessing the expected value. One was an approximation about zero return,
Mm-hmm.
which is the one you quoted before that's used in that table, and then the other is an approximation around expected return, which turns out to be much better and is applicable about a much wider range.
Mm-hmm.
So, for example, of the there are 5 chapters here.
Mm-hmm.
Chapter 1 is explaining why I believe in expected utility.
Mm-hmm.
Chapter 2 is a survey of mean variance approximations to expected utility of
Mm-hmm.
various kinds that different people have done over the years. It's a vast literature which the textbook writers don't seem to have any knowledge of. Then chapter 3, I just happened to have had tables where you knew where I had the Ibbotson tables where you knew the arithmetic mean, standard deviation,
Mm-hmm.
and geometric mean, which is the anti-log of the
Mm-hmm.
expected log.
Mm-hmm.
So I really had, and so I did. There's various rules around for going from the arithmetic mean and the standard deviation to the geometric mean.
Mhm.
The inputs to a mean variance analysis has to be arithmetic mean, because the arithmetic mean of a weighted sum is the weighted sum of the arithmetic mean, but that is
Mhm.
not true for the geometric mean.
Mhm.
So you got to have your inputs are arithmetic mean, your outputs are arithmetic mean, but what you get in the long run is the geometric mean.
Yeah.
Okay, so there's half a dozen different approximations, and I had these two historical databases. One is the standard asset classes,
Mhm.
stock, the SBBI stock, and the emerging market and so on. So I see, and then there's the 100-year, the London Business School has this Triumph of the Optimist, for 16 different countries, like
Mhm.
19 countries. They had 100 years of returns on their equity, fixed income and equity, real and so on. So I, since the period I was using included the hyperinflation of Germany, where you could get 1 billion% on your portfolio or whatever,
Yeah.
so I used real returns, and I saw which of
Yeah.
these 6 different ways of essentially looking at the arithmetic mean and standard deviation and guessing at expected log,
Mhm.
which of those 6 did best, and 3 got eliminated and 3 were pretty good. I mean, were good enough,
Yeah.
of which the Markowitz's second, the Markowitz 1959 second approximation around E was one of the one around 0 was the first eliminated, it was
Yeah.
lousy, and the one around E was one of the 3 winners. And in
Around
fact,
expected return.
around
Mhm.
expected return, and you could prove, mathematically, that of these 3, it was always the middle one. It would always give the middle estimate.
Yeah.
So, then I thought, everybody keeps talking about, you should use VAR or conditional VAR or semi-deviation is from chapter 9.
Yeah,
of the-
that's right.
Okay, well, I got these databases. Why don't I see mean and measure of risk, which measures of risk do best in going from expected return and that measure of risk to expected log. And lo and behold, it turns out mean variance does a little better than mean semi-variance, which does better than VAR, and
Yeah.
VAR is terrible.
Mhm.
VAR is terrible. You know why VAR is terrible? Think of Germany, which
Mhm.
had its maximum loss over this. Post World War II, Germany lost like 90% of its value,
Mhm.
and Japan 80% of its value, and Italy 70% of its value. More or less.
Yeah.
Which means that if you start a world war, and you lose, it
Yeah.
is detrimental to your wealth. Anyway, so here are probability distributions, which have one observation out of 101. It starts at 1900, goes to 2000, so it's
Mhm.
101 observations, where there's a 90%
Yeah.
outlier, which is way up. And it turns out that the mean variance approximation does great on these asset classes, and for most countries it does great, and for
Mhm.
Germany and Japan it does okay. It does
Okay.
okay.
Yeah.
Sort of okay. And so that was actually chapter 3, but chapter 4 it was. We're talking about comparing with other measures of risk. Well,
Yeah.
VAR tells you what the 5th worst of the 101 was. Let's say it's 100. So it'll tell you that it's a measure that looks at the 5th worst, but it doesn't look at the worst.
Because we're looking at the
And-
5% tail.
Yeah, it just says the 5% tail starts here. Now,
So-
CVAR does a little better, but
Mhm.
it doesn't. So VAR turns out to be lousy. And the final, may I see the book?
Yeah, here it is. It's a great book.
yeah,
I
thank
highly
you.
recommend it. It's one of my favorites.
It's about, the volume 3 is about half the, volume 3 has twice the word count, so it's going to be a fatter volume, just turns out.
Taking up more room on my bookshelf.
Alternate measures of risk, Conceivably, caveat and conclusion.
Yeah.
Conceivably, some other function of semivariance, MAD, mean absolute deviation,
Mhm.
VAR, and CVAR would perform better than those tried here. Conceivably, the ordering of root mean squared error for the functions considered here would be quite different. We did, mean variance is wonderful, for a different database or a different approximated utility function. That remains to be seen. If such is to be shown, proponents of the alternative risk measure need to get beyond their current line of argument, which goes roughly as follows. Return distributions are not normal, therefore mean variance is inapplicable, therefore my risk measure is best.
So those other arguments are the
Yeah,
groundless
it's
because
put up or shut up. Yeah.
mean variance does not
Yeah,
assume
that's right.
normal.
I do not assume normal
Yeah.
distributions. These are not normal.
Yeah.
Chapter 5 says, what are these distributions?
Yeah.
There's a broad class of distributions called the Pearson family,
Mhm.
and it has a special case of normal and
Yeah.
chi-squared and beta the first
Yes.
gamma and so on. It says, what, and it turns out that of the 19 countries, the first it was 16. When I did chapter 3 and 4, there were 16.
It's the Eurozone.
What'd you say?
Now it's the Eurozone, 19
Yeah,
countries.
19 countries, right. It turned out that 3 were normally distributed.
Mhm.
Not as much Eurozone, but Australia's in there. And
3 were normally distributed.
3 were normally distributed. Most of the remaining, more than half the remaining, were log normal,
Mhm.
and the rest were screwballs, various kinds. Now the normally distributed ones, that were, I could show you. There's a chart that shows you where
Yeah.
it depends. It doesn't depend on the mean and variance. It just has to do with the third moment and fourth
Mhm.
moment. The ones which are could very well have been normally distributed was the United States, Canada, and Australia.
Okay,
Yeah,
Australia.
not Britain.
I was
I'm
going to say
surprised,
Britain,
not
yeah.
Britain.
Not
The-
Britain.
and
Well,
war-
because it
the
went
war.
through World War II.
I was going to say the war.
Yeah.
Yeah.
And then not Germany and not Italy. And
No,
not,
no. But you would that's interesting, Australia,
Yeah.
because
I don't know.
Interesting.
There's a table, a chart where you have the third moment on this axis and fourth moment on this axis, and the boundaries between Pearson of type 3 and Pearson of type 4 and
Mhm.
Pearson of type 5. And this little point down there, that's the normal. And here's 3 little things clustered here, and up here is log normal, and et cetera, et cetera, et cetera.
it's great.
Yeah, a lot of fun.
You are.